So here now, let's talk about turbines, which you can do the similar analysis with pumps. Okay. So here you have wind blowing in this turbine, and then we get electricity out. Okay. So what we're going to do is represent this turbine on the left to a symbolic form like this. Okay. So we have flow coming in. And then this state 2 is kind of the back end here, okay? And then we get power out. So for turbines, what we can do is we can assume a lot of things, all right? The first thing we're going to do is that Q net is relatively small, the heat transfer between your surroundings and your system, between your output and your change in enthalpy, okay? What was enthalpy? What is enthalpy? Okay, so not quite temperature, but internal energy, yep, and pressure over density, okay? So that's what you're going to have high pressures, all right, typically with these, and that's why your delta H is so big, okay? The kinetic changes and potential changes of this system for the fluid, okay, again, are small compared to the other ones, all right? And so we only have those two. Oops. Main equations down here, if you can see them. You'll have work, which is m dot, or power, which is m dot times H1 minus H2. Okay, this is typically the shortcut for turbines. Okay, just like you had a nozzle question where you could have Q, you might have Q. Okay. This is for one set of turbines. I think there's a homework problem that has like a double set of turbines. You make the whole system as one. And so you're going to have more terms down here. But for the majority of the point, for the problems, you'll see you have one turbine set, and then that's your equation there. Okay. If it's steam, consider an ideal gas, right? So what can you switch H1 and H2 to? CP delta T, yep. Now, do you have to? No. You can just go back in the tables and find those. That's fine. This turbine, they're used in the Rankine cycle, which is the steam power plant. Okay, so they take a turbine, they throw it in that cycle. They have two heat exchangers, and they have a boiler. So that's their cycle. But once you analyze this, you can figure out then how much output you're getting from your cycle. All right, so again, we're going to start with the first law and break everything down and then get to what we want. All right, so here you have compressors and you have pumps, okay? Compressors use gas, okay? So when you start talking about, we have turbines, which we get energy out. Pumps and turbines, you actually supply the energy in to get the fluid to move. Okay, so compressors are gas or vapors, and pumps are liquids. Okay, so that's the difference between compressors and pumps. Okay, but you do it the same way. You do it the exact same way you do a turbine. All right, and the schematic can be exactly the same, but now you have work in instead of work out, and this becomes a pump or a compressor. Okay. Okay, so you have refrigerant. 134A enters a compressor at 100 kilopascals and minus 24 degrees C with a flow rate of 1.35 meters cubed per minute. Leaves at 800 kilopascals and 60 degrees C. Okay, determine the mass flow rate and the power input to the compressor. And again, just as a reference, like they have typically in these systems pressure and temperature measurements. Okay. And what they do is now you can use the theoretical calculations that we're going to find now to figure out what the actual power input that you need. Okay, so if you figure out this power input, then you need to figure out how it's going to be driven, right? You might need a motor, so you got to size the motor. Okay, so that's what they do all these with. We have R134A, P1 is 100 kilopascals. T1 minus 24 degrees C. V.1 1.35 meters cubed per minute times 1 minute over 60 seconds. It's 0.0225 meters cubed per second. P2, 800 kilopascals. T2 is 60 degrees C. And again, remember that you need to convert kilo to your actual like Pascal or joules. Okay, so remember that. I see a lot of people had issues with that. So here's our sketch. Then we have flow in and flow out. So I call it E of the fluid or mass in, E of the fluid mass out. And let's label this in as 1 and out as 2. Okay, so let's just write here find m dot and Wn. And let's do some assumptions. There's no out for work. The change in potential of the fluid and the change in kinetic of the fluid or the mass, fluid mass, we're going to approximate to be 0. Okay? So it doesn't give you any diameters, right, of inlet or exit. It doesn't tell you velocities, so you can just say, okay, you didn't give us any, we're going to assume 0. I think on the homework, one of them, I think there is a velocity and a different diameter. Assume steady state, and Q net is 0. This doesn't tell us anything about Q. Questions so far? See how we set the problem up? And now we can get right to the first law. And just get right to it. So 0 equals Q dot net plus W net plus the summation of m dot times, what was it, H, and this is N, plus V squared over 2 plus GZ minus everything out. There's a few things we could cancel, right? That goes away. Those terms go away. We end up with 0 equals W dot in plus M dot 1 times H1 minus M dot 2 H2. What we do now is say conservation of mass and state that M dot in equals M dot out, and that M dot 1 equals M dot 2, and I'm just going to call that M dot. Then I can rearrange W in to be M dot times H1 minus H2. See how I did that? So let's make a heading, find M dot. That's rho times V dot. What's another way to write? Actually, let's put subscripts on here, 1 and 1. What's another way to write density? How do you know you're a gas? You don't know for sure. You could, but what was it?
Mass over volume.
Mass over volume. Okay, there's another way.
1 over V.
Yeah, that's where I was going. Why do we want that? Because where can you find that? In your tables in the books, okay? Find little v1. All right, well, we know that P1 is 100 kilopascals. We know T1 is minus 24 degrees C, is that right? Yep. How do we know what? How do we know where we are in the vapor dome? Way back in chapter 3, right? Anyone remembers what to do? Charts, but what do we need to look up on the charts? Yep, you are correct. But we have pressure and temperature. We don't have V. We're looking for V. So we can't check that. There we go. I think that's where you're going with. Yep. So P sat at the T1 is 111 kilopascals. So P1 is less than P sat. So we're superheat. So, Cameron, you can use ideal gas because you're superheat. That's fine. Or you can just find it on the tables. And V1 comes out to be 0.1947 meters cubed per kilogram. And this is table A13. Okay, so now m dot equals 0.0225 meters cubed per second divided by 0.1947 meters cubed per kilogram, and you get 0.1156 kilograms per second. Okay, then using the tables, table A13, you can find H1 to be 236.33 kilojoules per kilogram, H2 to be 296.81 kilojoules per kilogram, and this is after interpolation. I don't think there's much on, I don't remember if there is on the homework. But if you notice, these are huge, right? 236 kilojoules. So you can still multiply by 1,000. Okay, so this delta H is pretty big. And then we can finally now plug in what W dot is. So 0.1156 kilograms per second times, what do I have first? H1? Yep. H1 is the 236, right? Minus 296.81 kilojoules per kilogram times 1,000 joules per kilogram, or kilojoule, and you get 7 kilowatts, or 7,000 watts. Did I do my algebra right? Oh, hold on. Yeah, let's double check our algebra here. So bring it over. Oh yeah, it should be H2 minus H1. How come no one told me that?
Because I don't know how to actually algebra.
So this would be negative here. And positive here? Yep. Because when we get this, if we know it's in, it should be positive, right? Because we've already defined it as in. Because we know it's in, because it's a compressor. Yeah, if you find that your compressor or your pump, you shouldn't have any work out. Okay? That's only for a turbine.